All right, so I will start with some announcements. Not too much going on. I'm going to be revealing the next assignment later today. If it's not up by 5 o'clock for some reason, somebody should send me a very angry email and I will get it up as soon as I possibly can. I am also going to get a study guide to you by Friday because we have an exam a week from Friday. It will be on everything we've been covering since the last exam. Surprise, surprise. All right. Last time, we were in the process of talking about some automata classes and how we could look at them overall. We looked at the fact that we had DFAs and NFAs, so regular languages in one class of language, which is one class of automata. We had our deterministic pushdown automata, which were in another class. And we had non-deterministic pushdown automata as a third class. Then we looked at Turing machines and are trying to figure out the extent to which those are different from non-deterministic pushdown automata. We also were in the process of looking at Turing machines with some different options to them and trying to figure out if the computational power of these modified Turing machines were the same or different from our basic Turing machine that we talked about a couple of class periods ago. So now that we can determine if two classes of automata are equivalent, we want to be able to see what we can do to Turing machines to be able to keep that computation power the same, or if we reduce the computation power, if we add to the computation power. So as an example, we looked at the stay option. So a Turing machine in its base form could only move left or right. And now we were going to add the stay option to say after a particular read and write to the tape, could we just stay? And the answer was yes, we could simulate the stay by doing a left and then right or a right and then left, where the second move there was just a no-op in terms of reading to or reading from or writing to the tape. So we asked the question, does this increase the power of the Turing machine? And the answer was no. The exact mathematical proof for this was in the textbook, but I showed you the logic is just you add a secondary move regardless of what the input, the input would be on the tape at the cell that you move to. You just move back the direction you came from. And you have simulated the stay option. We also looked at a couple of other Turing machine models. One was a multi-tape model. Sorry, multi-track. I guess multi-tape, multi-track. A tape with multiple tracks. The idea was now that the read-write head looks at all of these tracks and reads a list of input rather than a single input. So over, in this case, 3 tracks of information, we would now read the list ABC at the current position of the read-write head. We asked the question if this was more powerful than our simple Turing machine, and the answer was no. How did we come to this? We said we can restrict the tape to be only unbounded in one direction. That's not why we said that. That was the next thing we did. But the reason behind this is that we could put the tracks next to each other. So we'd have cell 0, track 1, 2, 3, cell 1, track 1, 2, 3, cell 2, track 1, 2, 3. And now you know that you need to read track 1, move right, track 2, move right, track 3, move right, and now you're back on track 1 with the next. So you just simulate this one read as a sequence of 3 reads, and you would need to transform the control of your Turing machine to be able to handle that difference. But you can map one onto the other, which is why the languages that it accepts are equivalent. The last thing we talked about was restricting the tape to only one unbounded direction. So it's infinite just to the right. There's nothing to the left of where the Turing machine would start. We asked if this was less powerful than a simple Turing machine, and the answer was no. The reasoning for this, I introduced the concept of mapping the positive integers onto the integers, asking the question of whether which of those sets was larger. Everyone seemed to think that there were more integers than positive integers, and we showed that that actually wasn't true. That the size of those infinite sets are both the same size, which was a very counterintuitive result. So now we're ready to move forward. The next one that we will consider is completely separate tapes and read-write heads. So now we end up with something that looks kind of like this, where we have the control unit at the top, and now we have separate read-write heads that can move independently of each other, rather than together like we could in the last model, where the single read-write head over all of the tracks was moving either left or right together. Now we have separate tapes, separate read-write heads, they can all move independently of each other. What do we think? Does doing this lead to a more powerful or capable Turing machine than before?
Would they do things like independent of each other? Would they do that deterministically?
It would need to be determined, yeah, in the control.
I think so.
Yeah, so now instead of having a single destination, you would have a destination state, but that state would be deterministic for all of the moves of, so you'd move one head left, one head left. One head left, one head right. Some combination of those. What do we think? Now we have a guess. Anyone online with a guess? Anyone who just walked in the room with a guess of the question they don't know yet? It's a yes or no question. You have a 50-50 shot. You're right. Now the question is why?
You can simulate it with a Turing machine.
Yeah, we can simulate it with a Turing machine. How? Any guesses as for what that conversion would look like? Let's say you have a program written for a regular Turing machine. How could you simulate this program with a regular Turing machine?
I mean, it'd be gross, but you could do it with like a limiter to show the different tapes, and then you could have different states to show like what you're doing from both the tapes and the heads.
Yeah, yeah, I think just like before, you would want to overlay the indices so that you'd know that we had tape one, tape two, tape one, tape two, tape one, tape two, something like this. And then whatever moves we were doing with the two different read-write heads, we would just do sequentially with two separate moves, if there were two heads. But now if there are 3 or 4 or 5, there's still a way to, we have an algorithmic way to convert one to the other. And again, if you're curious about that exact proof, the textbook has it in more detail than you probably want to know and more mathematical detail than you probably want to read it in, but that's the basic logic. Now we're going to add an extra dimension to the Turing machine. Rather than having a one-dimensional tape, we are going to have a two-dimensional tape. So now the read-write head, instead of just moving left or right, can move left, right, up, or down across this infinite matrix. What do we think? More powerful than a simple Turing machine?
I think like if there's a way to actually map that, because if there is, then obviously it wouldn't be more powerful.
Is there a way to map that with a simple Turing machine?
I can't think of one off the top of my head, like it definitely seems possible, just thinking about it.
Anyone else with any input? How could you come up with an algorithm to iterate this space?
Check each column value for each row value.
If you try to do that, we know it's infinite in all 4 directions. So there's not really an easy place to start if we want to iterate an entire row. If we tried to iterate this entire row, we would never iterate the left side of this. We'd never iterate the next row or the previous row. And any other ideas? What would people do?
I have another dirty idea.
Yeah.
Where you can have limiters showing like if we're which like row we're on.
Okay,
And then we could say like skip until this character, but
we have to know how long the tape was going to be,
Right,
and I
so I
think at
feel
the
like-
start of a Turing machine, we don't know. We could go until we hit a blank. We said that once we hit a blank, we know we've reached the end of the input, because otherwise we'd have to search forever
yeah,
if
so
we
that
didn't
first
know
one
for
is
sure.
Unbounded, but could we do some mapping similar to like with the negative integer example, where we could say this expands out for like just ultimate like you did with negatives?
Yeah, so the way that I'm thinking of doing this is some kind of spiral. So we would start and spiral outwards from this location. And then we would still need some way to know that we are done, but that would at least allow us, given a particular cell in this 2D area, we would hit that eventually, regardless of where it is. Now, we'd have to come up with some separate rules for how we're going to handle blanks, because there's no guarantee now that once we hit a blank, that we're actually done. It could just be a blank at the end of that row. So some extra work would be needed for that, but I think that's the basic idea that's going to make it intuitive that yes, we can iterate an infinite two-dimensional space with some interesting algorithmic choices. So is it more powerful? The answer is no. So the takeaway from all of these examples of what we can do to Turing machines is that we can actually turn this basic system into a more complicated system that allows for more representation without actually changing the underlying theoretical power of the system. Which is a very intriguing result. It allows us to think about how can we augment our own computers, because it's not going to change the power of the programs that we can write for our computers. Any questions on any of these models of Turing machines, or why it doesn't really affect the simulation power, computation power, whatever the correct word to use there is? All right, we talked about a Turing machine as a deterministic automata. So what happens now if we introduce non-determinism into our Turing machines? So we've talked at length before about non-determinism and how that's worked in regular languages, how that's worked in context-free languages, but we made a bunch of mechanical changes to our Turing machines and none of them affected the computation power. What about now if we introduce non-determinism? So first of all, let's try to define non-determinism within the realm of a Turing machine. What would that mean? How would that change the internal state representation of the Turing machine?
Would it be the same as everything else? We can have multiple transitions from the same configuration.
Yeah. Yeah, so historically, we've only been able to take one state or a tuple that represents the state in terms of our context-free languages. We had a tuple of the internal state representation of the Turing machine and the contents of the stack, or the top of the stack symbol. And that gave us a state. So now, what is a state in a Turing machine? When we looked at Turing machine transitions, we looked at this. What was the left-hand side of one of the transitions? Because that tells us when we're in this state, we have a transition to this state, writing this character on the tape. So it's still just a tuple, but it's the internal state of the Turing machine paired with the symbol that is on the tape at the location the read-write head is currently pointed. That tells us everything we need to know about how to make the next transition. So state, tape, pair. If we allow non-determinism, what changes? I think Patrick alluded to it. We can now allow multiple transitions from the same state. So let's say we're in a configuration where we're in state Q0 and there is an A on the tape at the current location. A non-deterministic Turing machine would say, now we have a choice. We can either go left and at the current cell write an A, or we could move right and at the current cell write a B. Note that it's not possible deterministically to do both of those because different symbols are on the tape. But as we've discussed with non-determinism, this allows us to kind of simulate in parallel universes, or it allows us to simulate in ways that we try all of those moves at once. And if there exists a path that leads to success, then we will accept. But it allows us to design something that now becomes a search space that deterministically we would need to search. So parallel choice, this isn't mechanical. This is not something we could program a Turing machine to do, but we reach now a more theoretical argument of if we could create a non-deterministic machine that was capable of simulating multiple things at the same time, what would that look like? So again, nothing about the definition changes, except that the transitions are now a function. Note that any thread that either rejects or enters an infinite loop doesn't matter. With non-determinism, we can have an arbitrary number of these happening at once. So if there happens to be one of those threads that's stuck in an infinite loop, it's never going to accept. So we don't worry about it. We just know it hasn't accepted yet. If any one thread of all of these non-deterministic threads leads to acceptance, then we just stop the whole process and accept. So we just need a single thread to do that, just like before. So the argument for non-deterministic Turing machines, the deterministic Turing machine is going to be keeping track of all of these non-deterministic states on its tape. We're trying now to figure out if there is a difference between a deterministic Turing machine and a non-deterministic Turing machine. Are they computationally equivalent? If they are, then we need a way to simulate that non-determinism on the deterministic Turing machine's tape. So our deterministic Turing machine is keeping track of every possible non-deterministic state in some way, writing that on its tape. We look at all active configurations of that non-deterministic Turing machine. We're updating them according to the program of the non-deterministic Turing machine. So everything that's on the tape is a possible path through that non-determinism. With every single update that the non-deterministic Turing machine makes, we need to go make all of those updates to every possible thread that the non-deterministic Turing machine might be in when we do that. So maybe we're deep into a computation and there are 80 active threads running. That means on the deterministic Turing machine's tape, there are 80 representations of states of the deterministic Turing machine. So now we have to go through an update for the 81st transition. How many? We have a lot of different places to go update. So it's a big process, but it's very similar to some kind of non-deterministic search. Maybe a visual would help. How are people doing with that? So each state is like each instruction. Kind of. Each instruction would be a transition. I think would be the better way to think of it. So we have, let's actually draw this out. We have a single tape that is now going to be split up into sections that represent, this is non-deterministic path 1, non-deterministic path 2, non-deterministic path 3, 4, 5. So we discussed when we introduced this idea that it was kind of like cracking a password. Deterministically, we have to go check all the passwords. Non-deterministically, I tell you what my password is and all you have to do is verify it. How long does it take to do that? Well, you're doing all of one way to think about doing that is you're doing all of the possible branches at once. We've just reduced the possible branch path. So we would have some node of a tree that now branches into a bunch of possible places that represent the first character of the password. So we now have active threads for all of these. And then each one of these is going to check for every possible character that is the second possible character in the password. And you can see that for each move that the non-deterministic Turing machine makes, this is only in a 4 or 5 character world. And of course, passwords can be significantly more than 4 or 5 characters, but a deterministic Turing machine has to do some kind of search through this space. It's either going to do a breadth first search or a depth first search. For a password, it makes way more sense to do a breadth first search because unless there's a cap on the length of that password, the depth first search is just going to make an infinitely long password and we're never actually going to check anything. So we should probably check all passwords of length 1, all passwords of length 2, all passwords of length 3. Deterministically, we actually have to go through and check that. Non-deterministically, after the first pass, we've checked every password of length 1 in a single step. After the second step, we've checked every password of length 2. After the third step, we've checked every password of length 3. So if we're trying to simulate this deterministically, when we make a single change, like check this, check all passwords of length 1, and we're simulating that deterministically, then we would need to write and check the first character, 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 write and check the first character. Moving from this first level to this second level would now say, all right, now instead of having 5 sections here, we need to have 5 times 5 sections, 25 sections to this tape. So now I need to divide this tape into taking this and turning it into however many nodes there are here and check all of those deterministically to see if any passwords map to the passwords of length 2. But the idea is it is possible to construct such an algorithm that would convert this to that. It would be highly inefficient, but it is possible to do so. Theoretically, we don't care as much about efficiency. We kind of have a side note for efficiency. A lot of times we just care about, is it possible to do this? And the answer in this case is yes, we can convert this in a way that makes sense. Questions on this idea? How we would try to convert a deterministic, or sorry, simulate a non-deterministic Turing machine with a deterministic Turing machine. All right. If we take this idea and formalize it, we would eventually be able to conclude for every non-deterministic Turing machine, there exists an equivalent deterministic Turing machine. And that just says that we can convert a non-deterministic Turing machine into a deterministic process. If I ask you to verify my password, but don't tell you what my password is, it is possible to eventually figure out what it is through brute force. It's not efficient, but it is possible. The next thing we want to talk about is the concept of a universal Turing machine. There is still, and I'm curious to see if people can think about or find what this is, a big difference between Turing machines as we've discussed them so far and the modern computer. Can anyone think of what that difference is? What can the modern computer do that a Turing machine, as we have discussed, cannot do? There will be a way to make it work.
solve multiple problems at once.
I think we kind of simulate that as well by having multiple CPUs. It's the same as I could grade multiple tests at the same time. I just need to have multiple TAs. You can work on multiple assignments at the same time. You just have to get one of your friends to do one of your classes' work for you. So a Turing machine program, as we have written it, is finalized. The modern computer is reprogrammable. We can write a new program, whereas the control unit in a Turing machine doesn't really tell us, doesn't really allow us to do this. we can't simulate computation. We can only perform computation, if that makes sense. So what we want to do is find a way to reprogram our Turing machines. And the solution to this is just allowing us to take as input another configuration of a Turing machine and a representation of the tape for that Turing machine. If we could take as input a Turing machine and a tape into a Turing machine, then we could find a way to simulate the computation of that Turing machine in this Turing machine. Could we find a way to read what that Turing machine does and do that with a Turing machine? Does that make sense as to what that idea is? Because that's what a compiler does, right? It's going to take as input some program in some language and simulate, is it possible to do this? Well, we'll map it to a grammar. But it would be nice to be able to do that. So a universal Turing machine is just a concept that allows us to represent that. And this is the next point that we can come back to if we have time and interest. The results of this showing that we can, in fact, represent this information and do this process is any Turing machine is finite in size. So we're going to feed it in as a binary string. If there is an encoding of a Turing machine, we can now read this binary string and decode it. We'd have some program that decodes the Turing machine to give us the unique computation that it performs. We know that a Turing machine can emulate another Turing machine. We talked about this and showed that we could, given one, we could simulate what the other is doing. We can simulate the instructions of that. Now we have a proper model of a computer. Now we can do everything with a Turing machine that we can do with a modern computer. Questions on that idea? All right, before we move too far into the next area, I want to take a brief aside and talk about something that you may have seen in discrete and you may have not. I get a lot of different answers when it comes to what people have seen in discrete here. But who here knows the difference or has heard of the difference between countable and uncountable sets when you talked about set theory? Looks like next to nobody. Excellent. So we'll start with a basic question. What is a set that is countable? Give me some set or maybe even the basic idea of a countable set. It could be finite. All finite sets are countable.
Would it be just an unpredictable set, like the set of integers?
Yeah, so some way of determining what the next one is going to be, even if it's an infinite set, like the set of positive integers, it's countable because we have a function that tells us what the next one is given the current one. The successor of 1 is 2. The successor of 2 is 3. The successor of 10,703 is 10,704. So the set of positive integers is countable. We all agree with that? Even though it's infinite in size, we can iterate it. Another way to think about that is there exists no positive integer that this algorithm would not eventually reach given infinite time. If I said the successor of a number is 1 plus that number, then there exists no positive integer. You couldn't give me a counterexample of an integer that I could not reach if I applied this function over and over forever. How about the set of positive even integers? Is this countable? Yes, now instead of just adding 1 as the successor function, we're going to add 2 as the successor function. Great. The set of all integers, I spoiled this. I'm a little bit mad at myself for doing that at the end of the last class, but is the set of all integers countable? What was that idea? Does anyone remember what that idea was?
It was that instead of like going left and right, you map them like alternating, so like one's positive, one's negative. Just
Yeah.
with it.
Yeah, so we're gonna have 0, 1, 2, 3, 4, 5, -1, -2, -3, and so let's just do that. So this order now would be 0, 1, -1, 2, -2, 3, -3, 4, -4, 5, etc. And this would hit every integer regardless of positive, negative, 0. We just have now a mapping that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Your task now is to come up with the function. Given one of these or one of these, doesn't matter which direction you go, how do you get the other one? How do we go from 5 to -2? What is the function that takes as input this and spits as output that?
It'd be integer division by 2, and if it's odd, flip the sign.
Yeah, how do we simulate if it's odd, flip the sign?
Well, I guess it wouldn't be integer division, you'd see if there's a decimal then.
Yeah, so we would basically find a way to say like -1 to the n. So it's gonna be -1 times -1 is positive, times -1 is negative, times -1 is positive. So you just continue to multiply the past result. If we're trying to find the successor function, you just multiply the end result by -1. Add 0.5, take the floor. That'll do it. So we'd have like -1 to the n, and then this is gonna be this value, the input value. Over 2. Integer division.
Dropped on the floor.
So we have a way now to get from this set to this set. This shows that it is also countable. All right. Some more fun ones. How about the set of all rational numbers? First of all, what was a rational number?
Any number that can be represented by a fraction.
Yes. Any number representable by a fraction. So 1/8 is rational. 1/9, despite being an infinitely repeating decimal, is rational. 10/3, despite being an infinite number, is rational. Is the set of all rational numbers countable? The nice, whatever my intuition is, it's probably wrong, so I'm gonna go with the opposite of it. I love that. Any other guesses? So we have a guess for yes, because we think it is no.
I'm thinking no, just based on the property of decimals can be infinite, and I feel like that's just, there's always just like some way you can make something smaller so you can't find the next one.
Okay, that's interesting. So there's no way to find something like the smallest possible real number. But is the smallest possible real number rational? Well, first of all, there's no such thing as the smallest possible real, or the closest real to 0. Anything that we could find, we could just add another 0 in front of it. But this actually is countable. Now that I've told you that it's countable, what's the algorithm? How could you write a program to spit out more and more and more and more rational numbers, but have no possible counterexample where I say, given your algorithm, I can give you a rational number, your algorithm should eventually output it.
So can the algorithm like check to see if it's good, keep going if it's wrong?
Should it need to? If it has a way of just generating more and more new rational numbers.
Well, what I was thinking is like, just to solve that, like a number can be as small as you want it to be a problem. You could just like check like 1/9 to 1/99, just keep going.
You could, but then would you ever get to 2/9 or 2/99? How could we do that? How could we write an algorithm that would output 1/9, 1/99, and also 2/9 and 2/99?
Without be deterministic.
Yes. Well, we know that if you can make it non-deterministic, we can make it deterministic just really inefficiently. So it doesn't technically have to be deterministic, but we should be able to turn it into something deterministic with a thought process. I'll give you a hint. Everything's quite so close. I'm representing these as N and D.
It would be like some binary search kind of thing. Or like you change the numerator to the denominator if you're higher than, well, I guess you don't know it, so never mind.
Do we agree that this is every possible fraction if both of these, if all the rows and all the columns extend forever? I have a two-dimensional representation of every rational number. We have 1/4. We have 3/2. We have 5/4 or 4/5. How could I visit every cell in this two-dimensional infinite table? If I pick a row and just simulate outwards, I'm never going to hit this row. If I pick a column and start simulating, I'm never going to reach the next column. What can I do? This is where having second grade artistic skills really comes in handy. The way you're going to do it is, Does that make sense? You're just going to iterate every diagonal. If you iterate every diagonal here as some process, each diagonal is finite length. So you're going to reach the next diagonal and then be able to continue doing that.
So it doesn't matter what order you do it in.
Correct.
Okay.
And do note that 1/1, 2/2, 3/3, 4/4 all represent the same mathematical idea, but putting them in a set, you would add it to the set and you'd only end up with one copy. But there is no counterexample of a rational number you could give me that this process would not eventually reach, given some finite amount of time. Even though there are an infinite number of rational numbers, again, you give me a rational number, I tell you how long it's going to take this algorithm to get there. And that determines that it is countable. Does that make sense? That kind of blows people's minds when they see it for the first time. But it's a very similar idea to iterating the infinite positive integers or the infinite integers.
I think my understanding of like what makes a set countable is a little off. So I was thinking that like if you were given like 1/999 to find out what comes immediately after that,
And you would have a way to do that.
So just like given like a, like 1/4, how would you know what comes?
So
immediately after that?
1/4. So first of all, we don't necessarily have to make it squiggly. We could change the directionality to always be. So 1/4, you would just keep track of in some variable somewhere. You would keep track of the current, I guess, numerator.
So does that have to be in order in terms of like ascending this in order in terms of where it goes in the stack?
Yeah, you need
Okay.
some function, some successor function that tells you where to go next, or some algorithm that tells you the process. And then in order for it to be countable, you just cannot provide a counterexample of something your algorithm would not eventually reach at output. So the successor function for 1/4, since this has become 1, we would write an if statement that says, if we reach 1, and we loop back around, add 1 to this. Start this back at 1, you 5/1, 4/2, 3/3, 4/2, 5/1. Now, because this is 1, loop back around, add 1 to this. You could write a program that would output all the rational numbers. Or at least start outputting rational numbers, always output new rational numbers and never terminate. But there is no rational number that that program would fail to output given infinite time to run. That's the big idea. All right. Next one I have for you is a question. What is a set that is not countable? Can anyone think of a set that you could not write an algorithm to represent?
Be anything without a pattern.
What would that look like?
Like
Would you give an example? But yeah, something without some kind of pattern to it.
3, 9, 52, -4.
So we would need some way of describing the set,
Okay.
or some way of describing the set that we're going to try to make.
What is actually part of the set.
Right. And then we would need some way to not be able to iterate over everything that is in that set. This could be a theoretical set. But we kind of have to be theoretical, considering that we can't possibly iterate over its contents. Any thoughts? Is there some set that you're aware of or have heard of that you just could not write an algorithm to output its contents? Patrick hinted at one of them. The set of all real numbers. So first of all, what is a real number? Yeah, so it's not complex. But any number, it could be an infinite number that's not repeating. So pi, for instance, is a real number, even though to the best of our understanding, pi is not rational. It doesn't repeat in any way, shape, or form. E does not repeat in any way, shape, or form that we are aware of. If we ever discover that it is, a machine stops somehow and says, we finished, we've calculated pi, then someone's immediately very rich. We've gone trillions of digits into the computation and still have no pattern.
So the rational part was the important part of the first one because you
Yes.
could map it out.
Yes, you could represent it as a numerator and a denominator. Whenever you have a pair like that, those pairs are iterable via some algorithm. But now a real, you can't represent it with a finite quotient, a finite numerator and denominator. Now it could be an arbitrary number. So for instance, there are an infinite number of real numbers between 0 and 1. You might think that you might have a reasonable algorithm for this by saying, all right, well, let's start with 0, 0.1, 0.2, 0.3, etc., until we reach 0.9. Now I'm going to iterate over all possible numbers that, so we'll start with 0.10. So 0.00, 0.01, 0.02, 0.03, all the way to 0.99. Then move on, 0.000, 0.001, etc. to 0.999. But will this algorithm never output? Do we agree that this is some kind of finite process, that this is possible to iterate? Did I do it? Did I count the set of reals?
If we ignore that, you need an rate for this to eventually work, but you never hit one.
We would never hit one, but yeah, let's just add it right here. Why not? Sorry.
0.12?
0.12 would be somewhere in here. This is everything that is a decimal representation that is 2 digits. There are 100 of them, according to this. Then there are 1,000 of these, to be 10,000 of these, 100,000 of these, but regardless, whichever column we're on, there'd be a finite number of them. What will this never output? Even something as simple as 1/9. Infinitely repeating ones. Everything here is finite length. Every one of these columns forever will be finite length. 1/9 is infinite length. Right? 0.111 forever. We will get arbitrarily close to 1/9 as we iterate this. We'll get closer and closer and closer with every column that we can iterate, but we'd never reach it. Get a better and better approximation, but we'd never reach it. So that is an example of a real number that will never be output by this algorithm. So we could say, sure, we'll append to these all the rationals. All the rationals that start with something, maybe. And then we'd have a way of maybe iterating the rationals between 0 and 1 as part of this. But then we would never reach any non-repeating numbers. So there are an infinite number of numbers like pi that are between 0 and 1, go on forever, and never repeat. This algorithm will never output those, regardless of what we consider. So I guess the question I would ask you with the last minute or so of class is, why do we care to distinguish these? The reason is we can prove countability by some kind of procedure. We write an algorithm as some kind of sequence, and we define how to generate the next term of that sequence, and we can show that there is no such number that is never output by that. But with sets that are not countable, we'll talk about those later. Countability, though, means it can be simulated by a Turing machine. So this starts to get at the concept of what is computable. We know we can iterate any countable set, be that a finite set or an infinitely countable set. We can iterate that. We can write an algorithm for it, and we can start a deterministic process that may not finish before the sun envelops the earth, but at least we can define the process. And if we had a machine that was significantly more powerful than our existing machines, we could get to any arbitrary endpoint arbitrarily faster. If we had a machine that was 10 quintillion times faster, then we'd be able to simulate everything that our modern machines could between now and when the sun envelops the earth in the first second. So it's worth at least theoretically thinking about what is computable, what is not computable, because what is computable will become possible with enough computation power. What is not computable regardless of how much power we end up having, we cannot solve those problems, ever. And they map directly onto whether we can count the set or not count the set of whatever it is that we're trying to represent. So I'll leave you stewing on that for the next day, and we will come back tomorrow and talk about this in more detail and apply it to the concepts of Turing machines in a bit more detail. I have office hours starting now in my office. If you have, I guess you can't possibly have questions about a homework because there is not one currently assigned. I will get that to you by the end of the day. It'll be due a week from tomorrow.
You don't have office hours starting.
You're right.
You have canceled it today.
I have canceled my office hours for the day.